Okay, so I'm happy to introduce our first speaker of the afternoon section, who is our own Alex Andoni, who's an associate professor in the computer science department here. And before joining Columbia, he spent several years at Microsoft Research in Silicon Valley, got all of his degrees at MIT, and was a postdoc at the Center for Computational Intractability at Princeton. Alex has made groundbreaking contributions to the algorithmic foundations of massive data, sublinear algorithms, high-dimensional geometry, and the theory of machine learning. He's one of the world's experts on nearest neighbor search and locality-sensitive hashing, which are methods with wide-ranging applications throughout computing and data science. And today he's going to tell us about how they're related to large language models.
Well, thanks for the generous introduction. Sounds like somebody else. Thank you. So I'll talk about nearest neighbor search, which is a problem I've been working for quite a while. But I'll focus on the LLM part. So let me start with the plan, kind of, right? So the preamble, kind of, right, will be talking about nearest neighbor search, what we have been doing, kind of, right? And I'm a theoretical computer scientist, kind of, right? So I view these problems as, theoretical computer scientists do, kind of formulate the problem. What is the best algorithm that works under worst-case assumptions? How can we formulate the problem to get such bounds? And I really want kind of a bounds which talk about query time, space, performance of the algorithm in general. Right, so I'll talk a little bit about that. And then I'll talk about, nearest neighbor search in LLMs, right? And there will be three parts. We'll talk a little bit about kind of, right, what LLMs, right, and where kind of, right, NNS nearest neighbor search kind of plugs into here. We'll, go over this picture a little bit later. Okay, but basically we'll talk about these RAG systems, which are like retrieval systems, and attention. Okay, all right. So that's the plan. So let's start with nearest neighbor search. Okay, so this is a data structure problem. Okay, so we're given, or indexing problem, right? We're giving a big data set of points, which we call P. Right, we think about this as a high-dimensional space. Okay, we want to preprocess, like do something, then somehow store this data set in a convenient way on, hard drive or something, or GPU. Okay, so but later we're given a query point. Okay, where is my clicker? Right, this red point here. Okay, cool. All right, and we need to report the point, let's say P star, which is the closest to it. Okay. And you should really think about this as we are in high-dimensional Euclidean space. This is kind of one of the most classic and standard settings. Okay, so this is so the distance that we measure here is Euclidean, but doesn't need to be. At some moment, I'll mention something else as well. Okay, and why are we caring about vectors which are high-dimensional, right? Maybe we don't need to say it today, kind of, right? But this problem has been studied for a few decades, kind of, right? The reason really is that these vectors come from, nowadays they come from deep embeddings of objects, right? So you have some objects, let's say, your data set is of images, right? And you want to do some kind of similarity or prediction about the images, right? Typically what you do, you would train some kind of model, right? That will represent these images as vectors, and the geometric information or structure between these vectors represents some kind of semantic relationship between these images, right? You can think about these images or documents or something else, okay? Right, and this has many applications, right? So first of all, nearest neighbor search it's a standard machine learning classification algorithm, right? So this is something that has been there for decades. And nowadays, this is, the classification ML is not done that way anymore, kind of, right? But the problem, the core algorithmic question still remains the same there inside kind of ML pipeline, as I'll explain a little bit later. Okay, so this has many, many applications, but it's also, in algorithm design, it's a central algorithmic primitive. Basically, as Andrew mentioned, right, I work in high-dimensional computational geometry in general. So for most problems, or many problems in high-dimensional computational geometry, they are one related to nearest neighbor search. Either kind of, right, you can use nearest neighbor search as a primitive to speed it up. Let's say a bunch of clustering problems. In one way or the other, we would need to solve some kind of nearest neighbor search, or the tools that we develop for solving these nearest neighbor search problems are useful for developing our problems. And actually, I'll give you one example later. Okay. So let me talk about the problem complexity of nearest neighbor search, right? So to get it out of the way, kind of, right? And basically, the point of the slide to say is that, in principle, in general, this problem is hard. We need to kind of relax it a little bit. Just to kind of, put some numbers kind of here on the slide, just to have in mind, okay, what data sets are we talking about? What is high dimensional? A data set of 1 billion size is relatively standard these days, at least at the companies, right? To build the nearest neighbor search on a billion points. The standard dimension is, 1,000 is also kind of a very reasonable dimension, right? I mean, if you depends on your embedding model, kind of, right? But hundreds to 1,000. Okay, so what are the classic kind of algorithms? What is the most natural algorithms here? Is like, well, one is basically no indexing. This is like the algorithm of, be completely lazy, don't do anything at the beginning, right? Right. This is in some sense underprepared, right? There is no pre-processing. You just store the data set. This means that you have very good space, right? You just store the data set. And query time is, well, for every query point, you just scan the entire database and find the closest one and so forth. Right? So it takes time, which is linear in n, up to this factor d, for computing dimension, let's say. Okay, so we really don't like this, right? This is in red because this is way too large, right? We don't want that for a query, you have, I don't know, a Google search query, right? I mean, for that, you go over 1 billion documents, right? This is way too much. Okay, so you want to do some indexing so that you reduce this query time to what we'll call sublinear in n, in the database size. Okay, so the other extreme, right? I mean, you can design algorithms which basically are over-prepared, right? They kind of prepare for all possible queries, more or less, right? And, think about this as kind of full indexing, and this will be very efficient in query time, but the space will typically, for these algorithms, will be some exponential in dimension, let's say n to the d. Okay, let's say Venn diagram size. Right, so n to the d, I mean, obviously this is like way, beyond imaginable, right? I mean, we want something which is closer to linear in n, right? But this phenomenon of, something is exponential dimension is the curse of dimensionality. Okay, so the question is like, well, can we do better, kind of, right? I mean, can we do like best possible indexing, right? Where we have query time, which is just size of a query, and space, which is linear in n. That would be like ideal solution, right? I mean, okay. But even before asking this, can we even do a little bit better, right? Can we do just a tiny improvement over this kind of no indexing algorithm, right? Where the query time goes from n to slightly sublinear, right? Like n to, let's say, 0.99, okay? So it turns out that this question, in principle, is impossible, at least under what is called strong exponential time hypothesis. Okay, think about this as a stronger version of P not equal to NP conjecture. Okay, so we cannot hope to solve this problem in kind of full generality, right? So to study, now there are two options, right? Either you say like, okay, forget theoretical guarantees, right? But again, I'm a theoretician, right? The way kind of, right, we approach designing algorithms to say like, well, how can we formulate the problem so that I can still prove something about it, right? And a very successful theoretical framework to develop such algorithms was the approximate version of nearest neighbor search. To say, let's relax the problem to some approximation and solve that, and develop algorithms, right, and then see how they work. Okay, so here is the definition for approximate near neighbor search. Okay, this is, there will be two steps of kind of relaxations. One is that we will define a threshold version of it, which is I give a threshold r, and I want to solve an r near neighbor, which roughly is the following, right? I have a query, I have a radius r that I care about. Think about this as r is my threshold of similarity, right? So, I think about some kind of similarity kind of search, right? I want to find things which are similar to me. My R is the similarity radius, right? I mean, things within R are sufficiently similar to me. Okay, so now I don't need to find the most similar thing, but I just want to find something which is sufficiently similar. Okay, so this is not the approximate version yet. Right? So the red part is, this is a no kind of, right? This is not a good answer for us. Okay, and the C approximate version introduces, some kind of no man's land or some like indeterminate kind of region, right? So this is bigger radius CR. C is our approximation. Think of C as being, let's say, 2. Okay, and we're saying that green stuff is good for us. This is similar. Red stuff is not good for us. It's definitely dissimilar, right? And the gray band is like could go either way, right? If it makes your algorithm simpler. Okay. So in practice, even if you design kind of this approximate algorithm, right? I mean, in practice, typically you want to solve kind of exact at the end of the day, but you can use this algorithm as a filter, right? It will tell you what are the similar things. Maybe it will tell a few things which are kind of close to being similar, and you look over them and select the ones that you like most. Okay. Typically, these are randomized algorithms, right? I mean, let's say we have some probability of success here. We won't really go too much into it. And in fact, we can prove formal connection that you can solve the nearest neighbor problem, the original one that I mentioned, the approximate version of it, by reduction to this problem. So solving this problem will be good enough for our purposes.
Alex, so you somehow need to calibrate what the right R should be, though, right?
Yeah, think about this as you build a few such data structures and you try to guess what is the right R. But if you took R, which is too small, you didn't find anything which is similar to you say like, well, maybe I should increase R by a factor of 2. Right, so at least it's relatively easy to do this if you have, by scaling up with a log of the aspect ratio, right? If you know some kind of bounds where your approximate. So this paper's contribution is to be independent of the aspect ratio, really. Right? So it is like just a log n as opposed to.
The aspect ratio is the smallest distance to the largest distance.
Or just the bounds within it. So like I know that, yes, in principle, yes, kind of right, but you can also think about this as like bounds that my nearest neighbor is for any query is between this bound and this bound, for example. And that would be the aspect ratio. Okay, so this is the definition of a problem, right? And we'll be studying, well, I'll tell you a few solutions for this particular problem. Okay? Yeah.
How is this C approximate thing any different than just changing R?
It's the guarantee here is, so let me go over this guarantee a little bit. The guarantee is the following. As long as there is something within green ball, I'll report something which is either from the green ball or in this gray band. But if there is nothing in this green ball, but there is something in this gray band, I may or may not report this. I don't need to guarantee anything like that. So in some sense, you can think about it as follows. If there is nothing in this gray band, then solving approximate is the same as solving exact. But this gray band introduces some non-determinism kind of. You can either consider these points as being similar or dissimilar kind of. Either option is okay. Okay, so here is kind of a classic approach for solving this high-dimensional nearest neighbor search. This is more or less kind of a local extensive hashing, and its variations are basically the main tools for solving approximate nearest neighbor search in theory, at least. Okay, this is due to Indik Motani from '98, and basically it's at the end of the day it's a geometric notion, right? It's a mathematical notion. You can think about this as a map, as a hash map, kind of. Right? In computer science language, it will be a hash map that maps the points in high-dimensional space into codes. Okay, and geometrically, kind of, right, you can think about it as follows. This is purely a partition of a space, right? So this blob is my high-dimensional Euclidean space, right? And this is just a partition. You can think about a hash map. From points to codes as basically just a partition of a space. Right? This will be this part, for example, is the part of all the points that map to the same code, let's say 1, right? And this will be all the points that map to code 2, and so forth. Right? So this is just a map, right? And what it allows you to do is that things which are similar will now have the exact match under this map. Okay, so formally, this will be a map that maps from high-dimensional space into some discrete universe, such that for similar pairs, right, these are the points which are close, I have that their hash codes are equal, they're in the same part. Okay, so something like that, right? And for pairs that are similar, let's say that this query and this point P prime are like far away, right? Their distance is bigger than this like bigger radius, right? I want their codes to be different. Okay, so if we can do this, right, then it's easy to solve the nearest neighbor search. It becomes, what is called dictionary problem, or basically just build an index, right? You store for every code, you store all the points that are there, and for a query, you just compute its code and retrieve all the points with exactly the same code. Right? This is easy, kind of standard thing to do. Right? So this is illustration here. Suppose you have these 3 points. You build this index here, and for a query queue, you just go to the corresponding bucket, and if this is satisfied, right, then you'll find here exactly the points which are similar. Okay, maybe maybe you'll find the points that are similar, and maybe you'll find points which are in this gray no man's land kind of, right, this middle territory, right? So this is why you have some non-determinism which point you'll return. Okay, but I'm sure many of you have seen kind of space decompositions before, right? I mean, of course, this is not possible to do such that it's satisfied for any points P and Q. Will be, there is boundary here. So if you take 2 points on 2 different parts of a boundary, right, this will be close, but this will definitely not be the case, right? So it's not possible to guarantee this, right? So you basically build a randomized map. So think about formally, this is a distribution over maps G, such that the probability that they collide, that we have the same code, is not too low, kind of it is some probability. But the probability that they collide when the pair is dissimilar is much lower than this one. Okay? Pictorially, you can think about it as follows. We want a distribution over these maps, over this space decomposition, such that as a function of the distance between Q and P, the probability that we have the same code, that we're in the same part, right, is decreasing. Right? And ideally, we want something which is kind of sharply decreasing, right? But in principle, this is kind of a prototype for the solution. Okay, so now this means that maybe because this probability is not too low, building one index is not enough, right? Because like here, the query is just on the wrong side of the boundary. So you repeat this process a few times, right? This is a randomized process, right? So you repeat it a few times, build a few indexes, and hope that in one of the indexes you succeed to collide with your close point, this time, P. Okay, so this is kind of the prototype kind of the algorithms, right? And of course, the main question here is, how to build these space decompositions, these randomized space decompositions, right? How to do that? Okay, and this becomes basically a geometric question. Right? Okay, so some constructions, here is one construction that I'll show you. Kind of, this is like a very nice one, comes from this first paper that are Indik, Morlika, and Mirokni. Okay, where, let's say these are your points. What you do is you take a grid, you randomly shift it, randomly rotate it in Euclidean space, and each cell defines a part. Okay, so this is one way to decompose this space. It has some properties, and you can, going through this kind of algorithm that I mentioned in the previous slide, you'll get something like time, which is n to power rho, and space n to power 1 plus rho. So the space is a little bit more than linear, but time is sublinear for rho, which is less than 1. And the exponent rho, right? Rho is basically quality of this partition. Right? This is, all the algorithms look of this form, kind of. For this particular decomposition, you can prove that this rho is upper bounded by 1 over c for approximation c. So just, to give a concrete number for approximation 2, you get exponent, which is a half. So most importantly, again, your query time becomes root n, sublinear in n. Okay. Now, this is not, from some of you who have looked at these kind of questions, right? Will say like, well, probably this is not the best way to partition the Euclidean space. And indeed, you can do better. You can improve this quality to something like 1 over c squared, so giving exponent of 1/4. But basically, decomposing space into parts which look more like balls, high-dimensional balls. Okay, so algorithmically, this is kind of like an illustration of how you do it. You take kind of a grid of balls, you randomly shift them, and kind of carve out the ball iteratively. Okay, so this is a decomposition kind of it, where one instantiation of a decomposition of a two-dimensional space, but this really happens in high-dimensional space. So this is something that I did with my advisor a while ago. Okay, so this is nice, kind of, right? You can ask, is like, okay, this is cool, right? I mean, can you do even better than this, right? And the answer is no, right? This is an example of isoperimetry. And basically using kind of, for analysis, for example, you can prove that this is the best exponent that you can get. Okay? And in general, this approach, right, I mean, the VLSH yields the best known theoretical algorithms for nearest neighbor search. Okay, where we have guarantees for approximation and so forth. Okay, so this is what I wanted to say about nearest neighbor search, and now like I want to kind of obviously switch more to talking about nearest neighbor search in the context of LLMs, right, and how some of these ideas appear there. Okay, all right. So nearest neighbor search in LLMs, right, and part 1 will be for nearest neighbor search in what is called RAG system, right. This is retrieval augmented generation, but I'll explain in a bit. Okay, so roughly speaking, the LLM pipeline is kind of goes as follows, right? Let's say you want to do this kind of query, right? I mean, it's like, so, I have papers, and I want to find something that I proved in those papers, let's say, best LSH bounds, right? So take all the papers, right? I mean, okay, this is not representative. I have much fewer papers than that. And what you take all these papers and your query, and you feed them into ChatGPT, let's say, right? Okay. Now, the problem is that this is big, right? And it typically breaks the context, you might have heard about kind of, the issue of the context, kind of, right? If the context becomes too big, it doesn't work as well, right? And, this might not fit in your context, right? So it will not work. So the systems, like the way we do is really is a little bit kind of more nuanced, right? I mean, not to feed this entire corpus of data into your LLM, into your transformer, right? So this is roughly, I mean, there are, you decompose this LLM pipeline into two pieces, right? This is like simplified, right? But it's a reasonable simplification. So your documents, right? Here are your documents. You feed them into this RAG system, this retrieval system, right? You pre-process them, right? So that comes of the query, which is this one, right? The query in this RAG system, it will find the most similar documents to this query, right? So it said like, oh, you're talking about LSH, let me pull out all the papers about LSH, right? So it will choose from all this corpus of document, just top key documents, basically. And these ones will be fed into your, context of the chat, for example, right? And this is a picture of a kind of transformer, but we will come back later in part 2 and 3. Okay, but for now we'll focus on this one. Right? And you can see that basically the question here is that, well, I take these documents and I, pre-process them, right? Do these embeddings, right? And then when given a query, I basically run a nearest neighbor search algorithm at the end of the day. Okay, so this is how nearest neighbor search is used in these RAG systems nowadays. But there is not much more to add, kind of like, how it is used, right? I mean, it's pretty much used directly, kind of. What I wanted to mention is somewhat different aspect of it, that in RAG systems nowadays, there are many algorithms, right, and many implementations of nearest neighbor search algorithms, right? And one thing that has emerged in the last years is that the most practically fastest algorithms and preferred in practice nowadays are algorithms which are unlike what I mentioned before, and they are basically the graph-based algorithms, right? One example of it is what is called HNSW algorithm, which roughly works as follows. Right? You take your points in the high-dimensional linear space, and you build a graph on them. So what you mean by build a graph of them, there are obviously different variants of it. But for every point, you kind of connect to a few closest points with some properties, and you build a graph that perhaps looks like this. Now, when the query comes, how do I find my nearest neighbor? Okay, so suppose my query is here. So what I do is that I have some start node. Let's say this purple node will be the start node, really. And what I do is that starting from this node, I go to one of my neighbors, and I go to the neighbor which is the closest to the query. Right? So if you follow this procedure, when you start from here, you'll go here, because out of all these neighbors, this one is the closest to the query. Then you go to this one, then you go to this one, then you go to this one. And that's it, kind of. And say, like, this will be my nearest neighbor to this particular query queue. Okay? This is a very different style algorithm than what I described before, kind of these hashing-based algorithms or space decomposition. And there is one question. I promised that I'll mention some open questions, kind of, right? I mean, this open question is perhaps more higher level, kind of, right? But an important question here is to understand why do these algorithms work so well in practice. Okay, there are. These are like some of the companies whose primary business is about nearest neighbor search. I mean, it is called vector search, maybe oftentimes kind of in industry, right? And I just use nearest neighbor search as kind of historic name for this problem.
I guess the success of this really depends on the graph having some nice properties, right? You could end up with loops where you always try to
Right. So the question is how to build graphs so that you have something like that, right? But also, once you build a graph that doesn't have, I mean, it won't be a loop if you always move towards closer to the query, right? Because you have always a potential function that is decreasing.
If you remove the second of
This one?
the connections, the second of the purple arrows, that gets removed.
This one, right? Then probably it will go to this point, right? And then, probably maybe this one will be closer, kind of, right? It depends exactly, right? I don't see immediately what is the distance versus this. But yes, in principle, it can get stuck. You're right. Yeah, it can supposedly, right? Okay, so suppose this green node wouldn't exist and this one wouldn't exist, right? This goes to this one because it's closest to the query. And for this yellow point, if only these two are neighbors, when you get it stuck in local minimum. Yes, exactly the point, kind of, right? I mean, it is much harder to analyze this kind of graphs because one, you shouldn't get stuck in local minimum, kind of, right? And the other part is that they work very well, right? As in they are very performant. And it is not very well understood, right? So let me say there are some work, right? So let's say that there isn't any theoretical work whatsoever. There is some work of the following form that say that suppose my data set has additional property, namely it has small doubling dimension, right? So I won't really define doubling dimension here, right? But think about this as like the degrees of freedom inside the data set, right? Suppose it's maybe 1,000-dimensional space, but it really lives on a manifold of dimension 10 only, right? So this is kind of smaller, like intrinsically it's a smaller dimension, right? So this is lambda is this smaller dimension. Okay, so what we proved is that you can get query time which is exponential in this doubling dimension. Okay, so there is a curse of dimensionality still, but at least it is only with respect to this doubling dimension, which we assume it is small. Right? So, right, this is proven for some versions of the algorithms, right? But for example, for the classic problem, versions of these problems, the ones that are actually, of this algorithm, right, that are actually used, including this HNSW, you can actually prove even two-dimensional point sets for which your query time will be omega n, right? And pretty much for the same reason that you can design data sets where you will get stuck in the local minimum and will not be able to get anywhere close to the query. So, and also, like talking to a few people, kind of, right? The notion whether does the data that we get from these deep embeddings of the documents, for example, right? You have a big set of, billion vectors, right? Do we have small doubling dimensions so that, it justifies that, it's exponential in lambda? It's unclear, kind of, right? That's not, I don't hear people saying like, yes, the doubling dimension is really small. So it's not clear whether this is kind of a satisfactory explanation. Right, so the open question here is, basically, well, can we understand the performance of these graph-based algorithms? Is there a kind of a different property of a data set that maybe arises from these deep embeddings that allow these graph-based algorithms to work very well? Okay, so this is more, like, I guess, practice-inspired kind of question, right? And maybe kind of a little bit less formally stated. But I did want to say also a problem which is kind of more on theoretical side, and I can't state it formally exactly. But this is a question of designing nearest neighbor search for distances which are not Euclidean. So far we're talking, you take your document, you take the entire document embedded into a vector, you take another document embedded into a vector, right? And I want to say that those vectors are close if your documents are talking about the same thing. But of course, this is, this feels very naive, right? I mean, a document like a paper will talk about, I don't know, LSH, but also nearest neighbor search and applications and stuff, kind of, right? So this is not a very necessarily reasonable thing. So that justifies looking at nearest neighbor search under different metrics. So basically, do an embedding of documents, for example, into some other space under some different measure of similarity, right? And one very natural one is Wasserstein distance or optimal transport. Computer science is called Earth-Mover distance, okay, which is roughly the following. So suppose you have document A. So instead of just producing one vector, you produce a few vectors, these green vectors, which kind of represent the few different topics that appear in this document A, right? And the same with document B. And I say, like, well, now similarity between document A and document B will be minimum cost matching between the green points and the red points. Okay, so this is kind of like a kind of less naive way to compare the similarity between documents now. Okay, so kind of more aggregate in some sense. All right, so now one way to try to do nearest neighbor search for these spaces, right, and pretty much kind of like the main one, is to say, well, let me take this new space, basically this Wasserstein space or F-mover distance. We have clouds of points, right, and we measure somehow the distance between them. Let me take this and embed it, kind of in functional analytic sense, kind of embed it back into some space that we can deal with, let's say Hamming space or Euclidean space. L1 is just kind of more natural here. With small distortion, right, with small approximation, and then just use nearest neighbor search for the Euclidean space. Okay, and the thing here is that you can do this, right? It has been done before, right? And one can get something like bounds of the sort of log squared S approximation, distortion for embedding for documents that have maximum support S. Okay, and this implies sufficient nearest neighbor search, kind of, right? But just applying directly, kind of embedding plus nearest neighbor search algorithm. Okay. The embedding lower bound, you can prove, there's a paper by Kot Naor that prove a lower bound of omega log S. But one thing that is not known is that, well, it turns out that you can do a relaxation of embedding and consider what is called average embedding. And for average embedding, constant approximation or constant distortion is possible. Okay, just to contrast, there was a very nice result by Asaf Naor a few years ago that showed that for any d-dimensional norm, it means logarithmic in dimension average embedding. Okay, this is much better than it would be kind of for standard by Lipschitz embedding, where the distortion is root dimension. So this is exponentially better, and that led to some nearest neighbor search algorithms for these kind of arbitrary norm spaces. Okay, so this is RAG. So let me talk about kind of the other side of the transformers, right, which is really kind of this part. Right, so I'm not gonna, this is a bunch of layers of, some kind of processing, right? And let's look just at one layer, really. And each layer, right, one of the kind of the main component of the transformers nowadays is this attention mechanism. Okay, so to define the attention mechanism, let me first define kind of a precursor problem in some sense, right? And this problem is the kernel density estimation problem. It has been studied kind of a while ago. And for those of you who have seen something like multiple method, think about this as kind of a form of high-dimensional multipode method. Okay, so the problem here, it's also kind of a data structure problem. And it says we have a data set P of, let's say, Euclidean points. And what we want is to preprocess such that for a given query Q, what I now want to compute is this function. Right? So this is the average over, we'll call them K from the data set, right? Mostly because this is the standard notation in the attention, right? Where these points are called keys. So let's go with that notation. Okay, and so we're summing up or taking an average over all the points in the data set, and we're computing the Gaussian kernel for it, right? So this is E2 minus the distance squared. Okay. And so this is a number between 0 and 1, and it has direct applications for some problems, right? But I'll mostly mention it with respect to attention. Okay, so this is the problem. What can we do for it? Okay, so again, kind of a simple approach to this problem is to say, let's just to estimate this for a particular query. I don't do any pre-processing. Let me just sample a bunch of terms here and just reweight accordingly, and this will be my estimate. Okay, and we're saying that suppose if this quantity, sorry, this should be KDE of change notation here. Suppose the KDE value, right? This value is at least mu, right? This is kind of our lower bound estimate. Then it turns out that taking something like 1 over epsilon samples and time will be enough to estimate this KDE value. Okay. So there is a theorem due to Charikar, Kapralov, Nuri, and Simenilakis, right, from a few years ago that showed that design an algorithm for this problem, for this estimating KDE problem, which improved the runtime to basically this one, like 1 over mu to much smaller power. So this is, mu is number less than 1. So this quantity is much less than this one, polynomially smaller. Okay. So we designed such an algorithm, right? But the point here that I wanted to kind of like highlight, I won't go over the algorithm, is that basically what it does it replaces this naive sampling with importance sampling, right? Because you say like, well, rather than sampling all of these, right, let me try to sample the terms which are bigger here, right? And note that the terms which are bigger here are the ones where these keys or these points are closer to the query, so somehow like connected to nearest neighbor search. So what they showed is that you basically can use locality sensitive hashing, kind of algorithm itself, to speed up this sampling, right? So the idea is, you partition your space, your query comes, it goes into this part, and you're saying, well, rather than sampling from all the points, I'll just sample from the bucket where my query lands in. Right? Those points are closer to my query, they should contribute more to the sum, so they should be more informative for estimating this KD value. Right.
So in this hashing, this is the sort of pre-processing that you're talking
Yes, the hashing will be pre-processing, right? The pre-processing will be that before I see the query, I partition the space and I put every point in each cell, kind of, right? So I organize the points in a particular way, kind of, right? So when the query comes and I say, well, now tell me all these points, take a random sample from here. Right? Do this a few times. And
the point is that the hashing can take a while. You only do it once.
you do it at the beginning. Yes, in some sense, yes. And hashing can take a while, but it's really kind of not a big issue because typically we can do pre-processing which is proportional to the space used. Kind of, right? So it is not a particularly heavy computation. Right? It's roughly proportional to what is the size of your index at the end of the day. It's not, in comparison to other algorithms like graph-based nearest neighbor search, their pre-processing is much worse, right? Because that pre-processing typically requires computing for every point, compute a bunch of nearest neighbors, for example, right? So it is kind of catch-22, right? And the original thing you have to do more exactly, kind of, right? Here it is mostly hashing, and it is pre-processing is much, much lighter, actually. Right? This is one advantage of this kind of algorithms.
When you do this hashing, for your grid lines, you need to determine who lives in each grid, right?
Yes.
So you still need to enumerate through all the points.
You need to enumerate for all the points, but you build an index on 1 billion points, you need to read them, right? I mean, somehow, like, you need to look at those points at least once, kind of, right? So yes, you do kind of a linear scan of your points at the beginning, but you can't avoid that, right? Because you have a data set that is, you're right. As opposed to the naive sampling where you don't need to look at everything, yes, you're right, kind of. In some sense, for naive sampling, you don't need to look at the data set. So this algorithm versus the naive sampling, I agree with more pre-processing happening here, more time spent on indexing. And yes, you're right, kind of, right? I mean, this is because we'll be using many more queries, right? So it is amortized. Okay, and just to go to attention mechanism, kind of, right? So I just defined the KDE problem, right? So this is the KDE problem, right? The first line. The attention is basically what I like to call it's a vector-valued KDE problem, right? So we are summing up, again, this looks like the KDE problem. Now, for every data set points, we also have a vector, a value vector, it is called. So we're summing up these value vectors with coefficients that depend on the kernel value of the query versus the key. Okay, and we normalize it so that we sum up these values from a distribution. Right? So you can think about this as this kernel defines a distribution over the value vectors of the entire database, and you just sum this up. Okay, so so this is the original KDE, right, and this is the attention mechanism. This is the attention mechanism, right? And I specifically kind of made it kind of look similar to KDE because it looks similar, kind of, right? And there is a natural question here: is what is the best algorithm for estimating attention, right? So what is the best algorithm for approximating this? We want kind of small space, small time. There is a lot of empirical work, especially reducing time and space. This is kind of like most of the inference time and GPU time and energy is spent on computing this, basically. Right? That's the heaviest part of the transformers, right? So this is why there is a lot of interest in reducing this. There is some theoretical work, including here by Josh Ullman from Columbia CS, who show that, for example, you can get good approximation if the norms of the queries are sufficiently small, or there are some, other kind of work, which would be more technical kind of to state, but which gives some kind of approximation guarantees, maybe as a function of the norms of the values of the keys of the queries, right? And so like I won't go kind of in more detail, but by and large, it is still not a problem that is considered solved in theory or in practice. Okay. So I feel like I'm at like 40 minutes roughly, right? I wanted to talk a little bit about part 3, right? If it's okay, kind of right for a few minutes. So part 3 will be looking at this attention computation problem a little bit differently, right? It says, well, can we replace the attention mechanism itself altogether? Okay. So one reason to do this is that here another paper here at Columbia, right, that by Allman and Yu, who showed that computing attention for n queries requires n squared time. So this is fundamentally you cannot speed up attention, right, if you are to compute it exactly. And even we also showed that even for some definitions of approximating attention, you cannot do this, or even some tasks that transformers can do efficiently, you cannot solve them faster than quadratic time, right? And therefore, you cannot speed up attention fundamentally. Okay, so perhaps natural question is like, well, can we change this attention mechanism to something else? Okay, and here is a framework in which we can approach this question. Right? The framework is as follows. Let's go to transformers, right? And we say, okay, we know that the transformers are in some sense too powerful, right? They have this attention mechanism that is quadratic time computation. You cannot speed it up, and it has the power of that quadratic computation. But most of the tasks that we care about shouldn't need really that much computation. So let's really identify what is like the relevant capabilities of transformers and then design some other mechanisms that retain those capabilities. Okay, so to identify the relevant capabilities, here is one problem, right? And this one task, right, that was identified and studied quite a while in the ML literature. It's called multi-step reasoning, right? So to give an example, you have something like this, right? John is in a playground, Helen is playing with John, a football is picked up by Helen. Where is the football, kind of, right? So you need to do kind of like, a few logical steps to deduce what is the answer to this question. Okay, so this is a task, right, that transformers are good at doing. You can mathematically formalize this as what is called k-hop task, induction heads, few names, right? Basically, you're given a permutation pi, right? This is a picture of it, right? Permutation pi, and an integer k. This is kind of like the hardness. How many reasoning steps do you need to do? You need to compute basically the kth power of the permutation applied to n. Right? So this means you start here, you look where it points to 6, you go to 6, you look where it points, you go to 8, look where it goes 7, and it goes here, and we found the answer, and this is my answer. Okay, so naive solution here is to say, well, let's do this. We can do this. We can solve this problem, right? We can design a transformer to solve this k-hop problem. And it will use k layers. Roughly, each layer of a transformer of this attention mechanism will do one hop, right? One reasoning step. Okay. So here is a theorem by Sanford, Tsu, and Telgarsky. Sanford and Daniel Tsu are here at Columbia, or were at Columbia 24 at least. Sanford graduated. They showed that transformers can solve this k-hop task with log k layers. So not k layers, but log k layers. The way they showed this is as follows. They said that an L-layer transformer, right, where you kind of combine these attention layers for like L rounds, can simulate parallel algorithms in some kind of standard model for parallel algorithms that have parallel time capital L as well. So in some sense, they have the power of simulating this. And there is a classic parallel algorithm that has logarithmic in k number of rounds of like parallel time to solve this k-hop task, this formal task. Right? And therefore, by their theorem, this means that transformers can also solve this problem with log k layers only.
Really quick question. It seems like going from 10, 3 hops was pretty easy for you. So why is this a hard problem? Why do you need to implement this through transformers?
Oh, why?
Or at least the ideal
Well, we want to build transformers, right, that can solve this kind of task, this multi-step reasoning. And I want it to, I have 10 layers, for example. I want it to solve reasoning tasks which are as many steps as possible, right? Where, let's say, and what we're saying is that if it is layer 10, there are 10 layers, let's say, of the transformer, then a naive solution, right, a naive way to imagine how to build a transformer to solve this task will only solve K-hop problems where you have only 10 reasoning steps. Whereas what this theorem says, you should be able to solve 2 to the 10 reasoning steps. So 1,000 steps, reasoning steps, right? So this is, I guess, that's the idea, right? Or put differently, to say, like, I want a K-hop task where K is 10, for example, right? Like, I want to be able to do, 10 mathematical steps, let's say, right? And I was like, what is the smallest architecture that I can build to solve this, right? I mean, of course, we want transformers with as few layers as possible, right? I mean, in part because, like, okay, we want smaller things, right? But also because the deeper the transformer, the much harder it is to train it.
But I guess, so in this formalized example, though,
Right.
is there really a reason to use transformers? Or if the point is to try to tell you something theoretical about how transformers could behave for the purpose of
In some sense, both, kind of, right? Because we know this was really kind of a point of identifying a capability. This is a task we can solve. If we want to solve this task, of course, we have algorithms to solve this directly, kind of, right? But one thing is that the transformers, there is a theorem, but also experiments. You don't need to tell it that this is the task. You just give it a bunch of examples of, here is a random permutation. For k equals 3, this is the answer. Here's another random permutation. K equals 3, here's the answer. It learns by itself, but it needs to solve the K-hop problem. And not only that, it learns an algorithm that does this with log k layers. So empirically, when you train it, it actually does it, finds a log k layer. So put differently, if you have 3-layer transformer, then it can do induction, like or K-hop task for k which is much larger than 3. Does that, I mean, yes, of course, if you know that this is to solve a task, right, we don't need transformers, right? But this is more about, here are transformers, right? We cannot capture all the capabilities of transformer because this requires quadratic time. This requires lots of resources, right? But we don't need to potentially, the real tasks that transformers are solving are not all the possible tasks, right? It's unclear that it needs to solve, the type of, tasks that are like really hard there. Right? This is a natural task that is kind of transformers should be solving, so let's focus on it. Right? This is roughly kind of right, this is a framework to study and to, somehow motivate, I guess, what will be the next slide, really. Okay, so in some sense, the point here was to identify capability to say that, well, what transformers can do is they can solve K-hop task in log K rounds. Okay, and more generally simulate parallel algorithms. So, so to do kind of the alternative architecture, right? You can say like, well, let us build a different architecture for transform, which is more efficient. It doesn't have this quadratic time kind of rate scaling, right? Maybe it will be more efficient to compute, and has the same capability, right? So this is a paper joined with Liu, Yu, and Samford, and Daniel too, right? Where we show that we can, we design kind of like an attention, which is kind of based on this notion of approximate nearest neighbor search, where in some sense, instead of approximating the attention, you define the model intrinsically, kind of, right, with approximation in mind to start with. And roughly the idea is that you replace the regular attention. You say, like, I don't need to compute the regular attention, right? Each my attention layer is not that, but it's an approximate attention to start with. And I say, like, I'm okay to have an attention which is some reweightening, some, convex combination of these vectors, right? But with these W's, which have much weaker properties, kind of, right? Like, maybe I don't have time to kind of to go through that, right? But this is kind of defining some weights which are not as smooth as these ones, right? I mean, they are much sparser, which means that it is easier to compute, but it's still enough. Okay, and the main theorem kind of proved that this is kind of a weakened architecture, which can compute everything that transformers can do, but they can still do, for example, they can still simulate all parallel algorithms in the same with a number of layers which is proportional to the parallel time of the algorithm. So basically, exactly the same identified capabilities that I presented on the previous slide. Okay, and the good part is that very efficient implementation of it is, basically using, this theoretical nearest neighbor search kind of algorithms, right? You can get runtime which is n to the epsilon per query as opposed to linear in n, which would be kind of the naive calculation of the attention. Okay, with the only caveat, right? Just to kind of finish here with an open question. You're right. Sorry.
Is there a good choice of these W's or?
No, so what I'm saying is that so I'm saying that the attention, in some sense, I don't specify completely the W's. I'm saying like the transformer should work as long as these W's satisfy these properties. Right? So in some sense, I have a relaxation to the attention. It says it doesn't have to compute this precisely. It is okay for it to compute it in some sense approximately. Okay, so that we can compute the attention, right? Whenever we do inference, for example, right, we can compute this formula much faster. That's roughly the idea, right? As in the attention should work from the beginning, as like it's baked into its design, the fact that the things that it will get will be approximate, as opposed to try to learn something which is kind of exact and full, kind of, right? But then when you do the inference, right, you switch the RAG under it and say like, well, now I will give you only approximate things. Right, and one caveat here is that in some sense it's like replacing that attention mechanism with like approximate nearest neighbor search. The only caveat there is that it needs to be trainable, right? As in the algorithm of approximate nearest neighbor search needs to be differentiable, and because at the end of the day for training you'll be running gradient descent on top of it, right? And the algorithms by default are not differentiable, right? There is no derivative of an algorithm that does an if and sums up things. Okay, so this is like a challenge here, kind of, right, to implement this kind of version of attention with a differentiable algorithm for approximate nearest neighbor search. Right, and this is not a completely crazy idea because there are related results which are very recent, right, which look at related problems, right, computing the distance from the query to a data set in a differentiable way, so defining a differentiable function that computes this. It has, let's say, bounded gradient and Hessian, right? This is what we'd like from a kind of differentiable algorithm. Unfortunately, this is kind of an algorithm that suffers from course of dimensionality, so as dimension becomes larger, it's exponential dimension. Okay, so let me finish with kind of the last conclusion slide. Sorry for running a little bit over. Again, talked about a little bit about nearest neighbor search, and these are kind of collected questions from the three parts that I mentioned, within this kind of LLM pipeline. So I'll stop here, and I'll be happy to answer questions.